Okay, so we'll continue exploring a little bit of Gromow's references on his article of simplicial volume and bounded cohomology. And today, specifically, we want to study a little bit of a Hitchin article called Compacts for Dimensional Einstein Manifolds. And we'll begin by saying a little bit of the examples, the most common examples of spaces that are compact four-dimensional Einstein manifolds. And the first one is simply flat Riemannian manifolds. So you're thinking about a 4 torus or a Cartesian product of 2 torus and stuff like that. The second is compact symmetric spaces. So you're thinking about spheres, a 4-dimensional sphere, or the Cartesian product of spheres, or projective spaces. And the third one was actually described by Burrell in 1963. Hitchin's article is from 1974. And that has to do with Clifford-Klein forms of symmetric spaces. So basically, you're describing a double or quotients of symmetric spaces whose universal cover is a non-compact symmetric space. You have compact manifolds whose universal coverings are non-compact symmetric spaces. So this will be compact Clifford-Klein forms. And these are not as geometric because you're mostly looking at quotients of matrices groups, with quotients with respect to the right action, basically. So now, a result from Berger from 1965 tells us that a 4-dimensional Einstein manifold must have non-negative Euler characteristic. And equality holds if and only if your manifold is flat. What we're doing is we have a couple of examples of compact four-dimensional manifolds, and we're trying to produce examples of spaces that cannot be endowed with an Einstein metric. And so we have this result by Berger giving us some sort of topological obstruction. For examples, here you have the connected sum of 2 for torus, which will have Euler characteristic -2. So it cannot be endowed with an Einstein metric. And you have S1 Cartesian with S3, which here has 0 Euler characteristic, but it's not flat. So it can't be endowed with an Einstein. Yeah, cannot be flat. So they do not admit Einstein metrics.
Why
Either way that I understood was
that's one of the typical problem already fixed.
The way I was convinced was actually by a theorem by Bierbach, saying that any flat, compact flat manifold can be finitely covered by tori.
Because the universal cover is not often. That's not how I'm doing.
Okay.
Right?
Yeah.
If it's flat, then it must be complete. So by Gata Hadamard theorem, the universe is covered by the explanation. Right? It's from Kenyon space cover the whole menu. Okay? And it's universal cover. So but topologically universal cover is R
Cross
times 3.
Yeah. Okay. Now, if your manifold is simply connected, then your Euler characteristic is necessarily positive. I couldn't find actual reference for this, so I was trying to work out. So we know that
Necessary positive or necessary negative?
necessary positive. So what I was thinking is
Euler characteristic of classes, okay? What is the definition?
so you have so you have B0 minus B1 plus B2 minus B3 plus B4.
Okay, here's the reaction.
You know that B1 is 0.
And B3 is not.
Why?
How can I theory?
Right, of course, yes. Yeah.
Theory. Okay.
And you actually know that B0 is going to be 1 because, so this is necessarily positive. So now the question is, can we find examples of simply connected compact manifolds that do not carry an Einstein metric? And this question was actually posed by Eels and Sampson. 65. What are the simply connected compact manifolds which do not carry an Einstein metric? And this is the question that Hitchin answers in this article. So for that, we have the first theorem, that if M is a compact four-dimensional Einstein manifold, with signature tau, and Euler characteristic E, then the absolute value of the signature must be bounded above by 2/3 of the Euler characteristic. So let's see.
Just don't have to play with the signature. In terms of curvature, right?
We're gonna get there on the proof, basically. It will actually use Pontryagin class, and then Hilbert signature formula. So we'll begin with the local orthonormal basis of one form. Then the curvature tensor is going to be written as a symmetric linear transformation of two forms. So it's going to act on EI's YJ's, and that's giving the omega j, which I can rewrite and basis as f of net r j r and now there's a result from Berger from 61 and Singer-Thorpe 69 that's about the normal form for the curvature tensor at each point of a four-dimensional Einstein manifold. And this result is key in the proof, and that's why this inequality star is sometimes it's referenced as Berger-Thorpe-Hitchin inequality. And this is saying that you can choose for at each point our basis can be chosen such that relative to the ordered basis taking E1, Y, E2, E1, Y, E3, E1, Y, E4. Now here it changes a little bit to E3 as E4, E4 Y E2, and E2 as Y E3. So with respect to this basis, are our curvature takes the form of a block matrix ABCA, where both A and B are diagonal matrices. So A is going to be written as lambda 1, lambda 2, lambda 3, and B as mu1, mu2, mu3. Now I have a few symmetries of our curvature tensor. For example, Bianchi identity. Which is going to tell us that the trace of D must be 0. Also, trace of A is going to be half of the trace of the curvature tensor, and here is 1/4 of the zero curvature. So to facilitate a little bit our work, we're going to denote the diagonal of A as a vector lambda, and of D as mu. Now, by Gauss-Bonnet, the Euler characteristic is given by integrating over your manifold the form 1 over 2 to the 4th pi squared 2 factorial of the sum of signal of the permutation JKL of sigma ij plus sigma AL. Now, using our form for the normal form for a curvature, this is going to be 1 over 4 pi squared sum of lambda I squared plus mu I squared, which I can write as 1 over 4 pi squared norm of lambda squared plus norm of mu squared. Now, the first Pontryagin class Pontryagin classes, you're looking at classes in rank 4 cohomology group. So the first is exactly at the top cohomology of your manifold. And this is going to be given by integrating over M the form minus 1 over 4 pi squared 2 factorial of the trace of omega squared. So it's going to be 1 over 8 pi squared, and the sum of R EI log AJ with R EI log AJ. Using our normal form for the curvature, this is going to be 1/5 squared plus lambda 1 mu 1 plus lambda 2 mu 2 plus lambda 3 mu 2, which is just 1/5 squared in the product of a vector lambda with mu. Now, norms of three-dimensional vectors and inner product we know how to deal with. So we know that the sum of the norms is bounded below by 2 times the inner product. So we have
Did you use the Einstein condition already?
the Einstein conditions comes from the normal form of the curvature.
Oh,
The Berger
yeah, that's right.
and Thorpe results.
Yeah. Otherwise, it's a tree. Yeah.
Mm-hmm. Okay, so then you can integrate both, compare, and you see that the Euler characteristic is larger or equal than half of the first contract. You can reverse orientation in M, and it's still an Einstein manifold. And the Euler characteristic won't change, but the contracting class is going to be the negative. So you have also that the Euler characteristic is larger or equal than half, negative half of the contracting class. So what we have is that the absolute value of the first contracting class is bounded above by 2 times the Euler characteristic. Now finally, by this signature formula, we know that the signature is going to be 1/3 of the first contracting class. And so we have inequality 1/3. Absolute value of the signature is less or equal than 2/3 of the yeah.
Otherwise, it's different. Right? How equals one third of T1 is topologically like only 2. Okay? So, contraction number of T1 is topologically
only. It's the mixture of also numbers. It happens often because
maybe easy to make it. Right? Because they're both from an index series. So it's contraction.
I figured out that the signature formula is actually, I tried to understand, but I need more time.
Based on this identity, the signature is also equal to integral recurrence. Right?
Yeah.
Right. So you can say the signature is still by that one.
We can just use this and reinstate this part. Yes. Right. So this finishes the first theorem. The second is if you have, again, a compact four-dimensional Einstein manifold,
theorem is more useful for the symplectic manifold. The comparison is positive, right?
Yeah.
Non-symplectic, then yes, and simply connected. Sorry, simply connected is more useful. Simply connected manifold, because in that case, all the numbers should be positive.
Or positive, yeah.
Okay, so then it's being called the useful. Okay, go ahead.
If M is, so if in addition to the hypothesis in theorem 1, M has non-negative sectional curvature, and this also works if M has non-positive, so we just have to not change sign. Then we can improve the inequality by saying that the absolute value of the signature is less or equal than 2/3 to 3/2 of the Euler's characteristic. And the proof is going to be similar with just a little trick. So in our normal form for the curvature tensor, our lambda 1, lambda 2, and lambda 3 are going to be critical values of the sectional curvature. So if M has non-negative sectional curvature, I want to consider my vector lambda. I want to consider no. If M has non-negative sectional curvature, then our vector lambda is inside the region of all coordinates being non-negative. And by the Bianchi identity, our vector mu is inside the plane given by sum of coordinates being 0. Now, if both lambda and mu are non-zero, then I can talk about the angle between them. And analyzing these two regions where they belong, this means that the angle between them must satisfy that cosine of theta is less or equal than square root of 2/3. It's at most square root of 2/3. So that we have that the inner product of lambda and mu is less or equal than square root of 2/3. norm of lambda, norm of mu. And this inequality.
So it's a good exercise for qualifying them.
Yeah.
I should have provided it.
Yeah.
Right?
Mm-hmm.
Label this.
Yeah.
Good.
And this, well, technically you could ask this also in analytic geometry. But yeah. Okay, and this inequality here with inner products still holds if lambda or mu vanishes. Now, the same as before, since the sum of the norm squared is larger or equal than 2 times this product, we have that the sum of the norm squared is larger or equal than 2 times square root of 3 over 2 inner product of lambda and mu. Still linear algebra bit. I'm just relating these two inequalities to relate the sum of the square of the norms with inner product, which were the two factors that appeared in the form we're integrating to get the Euler characteristic and the form we're integrating to get the signature. So the same thing, integrating, you get the inequality. And similarly for the non-positive sectional curvature, because then the only difference is the region where lambda is, but it's just mirrored. Okay, so examples. How can we answer a question of a topological space of a manifold, a compact four-dimensional manifold that cannot be endowed with an Einstein matrix, but is simply connected? So let our manifold be the connected sum of n copies of CP2. This is simply connected. The signature is going to be n. The Euler characteristic is going to be n plus 2. And by theorem 1, if M is Einstein, then the absolute value of the signature n has to be less than 2/3 of n plus 2. I believe it should be equal, sorry, which means that n needs to be less than 4. Okay, so I announced and proved the versions of the theorems that have only the inequality. The theorems from Hitchin also says about what happens in the equality case. So that's why strict inequality is here. So if you have a simply connected sum of 5 CP2s, then you know it's simply connected and cannot have an Einstein. It is 4, it also doesn't have. So 3 below. Now by theorem 2, if M admits a metric of non-positive sectional curvature, or non-negative, then the inequality we have is that n must be less or equal than 2/3 to 3/2 of n plus 2, which is strictly less than 5/9 n plus 2, and so n must be less or equal than 2. So that you know for the case n equals 3, your connected sum of CP2s can be endowed with an Einstein metric, but that Einstein metric is going to, the sectional curvature of that metric is going to change sign. So for the last few parts, what I'm going to do is go back to Gramont's article. So in volume, official volume, and bounded cohomology. We'll begin with the compact four-dimensional Einstein manifold. With Ricci curvature constant equals to -1. By Patricia torque inequality that we proved, Gramont improves a little bit this type of, actually modifies a little bit this inequality to say that your Euler characteristic is going to be larger or equal than an interpolation between the signature, the absolute value of the signature, and the volume of n of their manifold, where this theta has to be between 0 and 3/2. If it is exactly 3/2, then we have the inequality that we proved. And theta prime is going to be 1/48 pi squared minus theta squared divided by 108 pi squared. Now, in this article, Gramont has the main inequality. Saying that if M is complete and dimensional Riemannian manifold with Ricci curvature bounded below by -1, then the simplicial volume of your manifold is less or equal than a constant depending only on the dimension of your manifold times the volume of then using the Berger-Thorpe hitching inequality and this main inequality, we have the theorem that all compact four-dimensional Einstein manifolds satisfy that the Euler characteristic must be larger or equal than theta times the absolute value of the signature plus theta prime times the simplicial volume of your manifold divided by 216. This 216 comes from an upper bound for the constant n for dimension 4. And theta prime as above.
No, theta prime is arbitrary.
Theta prime depends on theta. So theta can be any number from 0 to 3/2, and theta prime is this function.
But every metric can normalize it to each group with it.
So they're all compact, yeah, four-dimensional Einstein manifolds.
So when the simplicial volume is larger than this is a very good strong couple.
Yeah.
So that means for the bad manifold is sufficient large in pi 1. Okay? Yeah, the sufficient large pi 1, maybe Euler number is not that large. Yes, suppose like a, well, if the manifold was, it'd be weird. If the manifold is a hyperbolic manifold, that's the worst case. In that case, is we can say Euler number is positive. Yeah, it's hard to understand relationship of just the body balance. Okay, but that clearly this works for compound manifold was very bad pi 1. Right, not for trivial pi 1. Pi 1 is trivial. Simplicial volume is trivial.
Yeah.
Right. And you still have to use right original code. Okay. How to do that? The pressure problem is less than equal C, and that's already known. Can you go back a little bit? Where the inequality using? Okay, this by projection inequality, you get this.
Sorry?
You get this inequality, right?
Mm-hmm.
How do you get this volume involved?
That's Gromov's
Of the dimension.
Yeah. So I think it's basically a type of interpolation, because it doesn't appear here, but when you're integrating the forms, it's that the volume of your manifold appears.
I see. So when Patricia is working on that, maybe he doesn't want to get a volume from above.
Mm-hmm.
But Rome said they're very happy to see that.
Yeah.
And you can always normal, this of course under the curvature condition, normalization, right? Is the metric, right?
Yeah.
Equal to n minus
Mm-hmm.
That's good. Can you find out the inequality?
Oh, right on. That's right. And that's how you realize how much Gromov's article is hard and dense. Yeah. Because this is like half a page in the article, and you need to go back to the original article. And
I think that for the Einstein metric case, number one, what is the Einstein metric? Okay, that's not clear. This should be the average of remaining curvature tensor, in my opinion, somewhere. There are many versions. Number two is even in three-dimensional case. Okay, we don't have we cannot show it's in three-dimensional case. If you can have an Einstein metric in some definition, okay, can you prove it has constant curvature, right? That's not clear. Okay, so that because no remaining quantity involved. Only that problem is solved, then you can start to work on four dimension.
And we don't, there's at least how to deal with contrarian classes.
Yeah, that's right. Of course, you can always assume it's being an Einstein if the rich curvature is constant in some rich curvature, and plus some non-remaining quantity vanishes. Then you still end up with the remaining metric. Then set it out. Right? Yeah. My proposal is find my proposal is find the rich tensor in vanishes and another constant curve, another quantity we call xk equals 0. And those two conditions will be enough to describe so-called Einstein metric. Other conditions are too strong. Okay. So and then you have to use a Bellwether connection. Finish the connection.